Check it.
Okay, welcome back. Today we're going to be solving systems again, but this time by elimination. Last time we did it with substitution, and with substitution, the idea was you had to have a formula. If you had a formula in one of your equations, or both of them, then you could use substitution. But what if you don't have a formula, okay? If you don't have a formula, then you don't want to create one that's going to have a whole bunch of fractions and a whole bunch of complication. There's another way to do this algebraically, another way to solve systems called elimination. Okay, so this is an Algebra 1 review yet again. You probably learned substitution and elimination together back then. I'm going to show you elimination now. Now, before we get into elimination, all right, let's talk about why elimination works. Okay, so elimination works because of the following property. Let's say you have an equation, 5 equals 5. I think everyone will agree that that's true. That's a true and valid equation. Well, if you take another true and valid equation like 3 equals 3, okay, pretty sure that that's valid as well, and you add the two equations together, just add them together. 5 plus 3 is 8 equals 5 plus 3 is 8. You get a new equation, and that equation is also true and valid. So the idea is adding together two valid equations yields another valid equation. Now let's say we have an equation that's true, like 5 equals 5, and we decide to multiply both sides by the same number. I don't know, -2. So let's multiply the left side by -2, and let's multiply the right side by -2. -2 times 5 is -10, and on the other side, 5 times -2 is also -10. So if you multiply an equation, 5 equals 5, which you know is true, by any number on both sides, you get a new equation which is also true. So let's just keep this in mind. Adding together two equations, you get something that's true. Taking both sides of an equation and doing the same thing to both sides, it also works for adding and whatever. As long as you do the same thing to both sides, it's going to stay true, multiplication included. So let's come down to here. So here's how elimination works. First of all, you want to put the equations, these are linear equations, you want to put them in what's called standard form. So we know how to use slope-intercept form, y equals mx plus b. That's slope-intercept form. But there's also something called standard form, which is ax plus by equals c, where a, b, and c are whole numbers. So you can see that this is 3, this is -1 here, and this is 15. That's your a, b, and c. A, b, c right here. 3, 2, and 12, -6, 5, and 30. You have all of these written in standard form. Okay, so if you have equations written in standard form, you can try solving by elimination, solving the system by elimination. Now here's what you want to do. The first thing you want to do, okay, in the steps here, step 1, make sure they're in the right format. Get rid of any decimals or fractions, and I'll show you how to do that later. And it's a good idea to have the first term be positive, but that's not really incredibly crucial. All right, let's see if we can eliminate one of the letters. Now, when we were substituting before, the thing that I said was you had to get rid of either x or y so that you could solve for the other one. For instance, you can't solve an equation that has two different letters in it. So if we can get rid of the x's in an equation, we can solve for y if we eliminate the x's. Or if we can eliminate the y's, we can solve for x's. You need to eliminate one of them. And with substitution, we learned how to do that. Well, with elimination, you're going to also eliminate one of the variables, okay? So here's the deal. You have two equations here, and you want to eliminate one of the variables. So what you do is you try adding the two equations together, because we saw that adding the two equations together gives you something true. So let's add these equations and see what happens. 3x plus 2x is 5x. -y plus +y, hey, they cancel out. They eliminate. There's the equal sign, bring it down. And then 15 plus 10 is 25. Now take a look. Did you eliminate one of the letters? Yes, you did. Okay, yes, you did. And now you can divide both sides by 5 and you get your first answer, x equals 5. Now you still need to find y. And unfortunately, unlike with substitution where you always had a formula waiting for you, with elimination, you just get to pick which one of these equations you want to plug the 5 back into. So let's say I use the top one here. 3x minus y equals 15. So 3, I'll put a blank where the x is supposed to go, minus y equals 15. and we said that x was 5. So this is the back substitution step. It's the same thing you do with substitution, where this in the second part, but you don't have a y equals function waiting for you like you did with substitution. Anyway, this becomes 15 minus y equals 15. We'll subtract 15 from both sides. We get negative y equals 15 minus 15 is 0, so y equals 0. So our answer should be 5, 0. Now we can check our work, because that looks like it, you might think, I don't know, why did I make a mistake there? Why is y 0? Well, there's nothing wrong with that, but let's try it. If x is 5, this is 3 times 5, which is 15, minus 0, which is 15. So that actually works in the top equation. And you can also try it in the bottom equation. 2 times x, which is 5, so 2 times 5 is 10, plus 0 is 10. Yeah, it actually works for both. So this is definitely the right answer because it works for both equations. And you can check your work just like that. Okay? Now, could you have forced substitution here? Well, you do have one of the letters by itself. If you remember yesterday's lesson, we would have subtracted the 2x to the other side and created a formula y equals 10 minus 2x. And then we could have done substitution because we have a formula now. But if you notice, this was really, really fast. I mean, all we did was add the equations together and bing, bang, boom, one of the letters disappeared. That was really the best case scenario. Okay? So sometimes elimination is faster than substitution. And in this case, it was. How about over here? Okay, we have two equations here. Now, let's say you wanted to use substitution. Could you make a formula out of any of these? The answer is no. None of these are by themselves. All the letters have coefficients. All the variables have coefficients. And even if you wanted to divide everything by a number, it wouldn't work out. Because let's say you wanted to divide by either 3 or 2 on top. If you divide by 3, you get the x by itself, but then you got 2/3 over here. That's no good. And if you divide everything by 2, that's going to be fine, but now this is 3/2. So you don't want fractions. Okay? And the same thing down here, divided by 6 or 5, neither, one of these is always going to be a fraction. So you don't have the ability to make a clean formula here at all. So substitution is out of the question here, but elimination is not. So once again, step 1, add the two equations and see if you get lucky. Does anything cancel out right away, like I did over here? Here we got lucky. Well, unfortunately, we're not going to get so lucky right away here. 3x minus 6x is negative 3x. 2y plus 5y is 7y. And 12 plus 30 is 42. Nothing canceled out. You still have two different letters, x and y, so this is not solvable. Okay? So since it's not solvable, we have to resort to the other trick. Remember I showed you that there was two things you could do here. You could either add the equations together, or you could multiply both sides of any equation by any number. Okay? So let's try that. What could we do there? Okay, that's not going to work. So let's see if we can make this work. How can I make it so that something will cancel out like that did? Okay? So you look over here and say, all right, this is a 3, this is a 6. They're not the same thing. They're not going to cancel each other out. This is a 2, this is a 5. They're not the same but opposite signs. They're not going to cancel out. But if I were to multiply this by a 2, wouldn't this become 6x? And wouldn't that cancel out the negative 6x right below it? So that's what I'm going to do. I'm going to multiply this top equation by 2y. So this becomes a 6x. Well, we have to keep going. This becomes a 4y. And this becomes a 24. Now with this new equation here, okay, just looking at the new equation, you can see these will cancel out. We will eliminate the x's. And that's exactly what we want to do. Okay, so I'm going to recopy the problem here. Okay, now that I've recopied the problem, we try going back to step 1, which is add the equations together. If I add these equations together, you can see now these do cancel out, and I've eliminated the x's. Okay, so what do I have left? 4y plus 5y is 9y, and 24 plus 30 is 54. Now I can solve this equation because there's only one letter in it, just the y. So I'll divide both sides by 9, and I get y equals 6. Am I done? No, because once again, I need the x and the y. So what you can do is come back to the original problem here and choose one of the two equations to plug in y equals 6. Okay, unlike substitution where you had a formula waiting for you for the x, this time you can just choose one of the two. It doesn't matter, whichever one looks easier to you. So the top one looks a little bit easier because the numbers are smaller and there's no negatives in it, so I'll use the top one. It's going to be 3x plus 2y, but I'm going to replace y with a 6, so leave a blank where the y is, equals 12. And we said y equals 6, so we'll put a 6 over here. So this becomes 3x plus 12 equals 12. We're going to subtract 12 from both sides. We get 3x equals 0. Looks like x is going to be 0 here. Divide by 3, x equals 0. So my answer looks like, alphabetically, x comma y is 0 comma 6. Now I can check my answer here, okay? And you really should check your work, especially on a quiz. Let's see if that works. If x is 0, this is 3 times 0, which is 0, plus 2 times y is 6. This is going to be 2 times 6, which is 12, and 12 does equal 12. So that works. How about here? Negative 6 times 0 is going to be nothing, plus 5 times 6, which is going to be 30. Yeah, this is correct. So both of our first two questions happen to have a 0 as one of the answers, as one of the coordinates, but that doesn't matter. Okay, we didn't do anything wrong. So this is elimination. Okay, in short, add the two equations together and hope that something cancels out. If something doesn't cancel out, make it happen by multiplying the entire equation. Okay, so here we have two more systems. We're going to do these systems. However, you can see that they have a bunch of decimals, and this one over here has a bunch of fractions. And before you start, once again, you have to put these into standard form, which is ax, some number x plus some number y equals some number c. Now, you know, if the a is 1, you wouldn't write it, you just leave it out, right? Or the b is 1, you wouldn't see it, but it would still there'd still be an x and a y. Anyway, you want to put it in standard form, and you want a, b, and c to all be whole numbers. So here you have decimals in this top equation here. How can you fix that? Well, you might have learned back in, I don't know, 6th grade or earlier, that if you multiply a number by 10, that it adds a 0 onto the end. And then when you got to science, you might have learned that if you multiply a number by 10, it moves the decimal point over one space. So for something like 3.4 times 10 to the third, okay, scientific notation, you would take the 3.4 and move the decimal point over 1, 2, 3 times, because this was times 10, times 10, and times 10. And you would get 3,400, right? So this is the same trick here. You're allowed to multiply this equation by any number you want to, but if you want to get rid of decimals, multiply by either 10 or 100 or 1,000, some multiple of 10, that will move the decimal point over so that you have whole numbers. Now I only need to move this decimal point over one time. Okay, there's no decimal here, but you know it's 6.0, right? Move that over. So multiplying by 10 will make this negative 1, 2 instead of 1.2. It just becomes 1, 2, which is 12. Negative 12 x plus, this becomes 3, 4, 34, right? Y. And this becomes 6 and then the 0 because the decimal point moves over, so 60. And no more fractions, no more decimals. And that's the trick there, okay? Now if you really want to go all the way and get this in standard form also requires that the first number be positive. That's not really necessary for this particular thing, but it's a good thing for you to know what standard form is. So how do we get this first number to become positive? You can multiply the entire thing here by -1, which means if you multiply the entire equation by -1, okay, on both sides, and distribute that -1 to all three of these, you get positive 12x, negative 34y, and negative 60. That is true ax plus by equals c standard form now, okay? And that's going to be our first equation. Now, what about the bottom one here? The bottom one doesn't have any decimals, so you might think, hey, it's good to go. Yeah, but it's not in the right order, okay? It's not ax plus by equals c. So if you try to use that now, it's going to be 6x. The equal sign is in the wrong place. You got the negative 30 over here, and you got your 17y over here. That's not, you're not going to be able to add that. You need everything to be stacked up, okay, in the same fashion on top and on bottom. So how do we get this thing to be standard form? Now you might notice that the 17y is not supposed to be on the right side of the equation. It's supposed to be over here on the left. That would make it standard form because it's supposed to be x, then y, then equals, then c, right? So how can we get the 17 to move over? Well, that's pretty simple. Just get rid of it, meaning subtract it from this side and subtract it from that side, from both sides of the equation. Now what you'll have is 6x minus 17y equals negative 30, and that's definitely in standard form. So I can put that over here. Okay? And now I have an equation, sorry, a system of equations that can be solved using elimination. They're both in standard form, ax plus by equals c, okay? And they're ready to go, and they're all whole numbers, okay? Okay, so let's do the first step. Step one is to say, do we get lucky? Let's take a look. If we add these right now, does anything cancel out? Unfortunately, we're not getting lucky with this one, okay? Okay, so since we're not getting lucky right away, we can make something happen here. I'm actually just gonna drag this down here a little bit so I can make some more room. And what can I do here? How can I cancel something out? Well, it looks like if I were to multiply the bottom by 2, this would become 12x, right? So multiplying the bottom by 2 would make this 12x. Would 12x cancel out 12x? No, it wouldn't. You get 24x. What you want to do is have a negative 2 make this a negative 12. They have to be the same number and the same letter, but they have to be opposite signs in order to cancel out. So I'm going to decide to multiply the bottom here by negative 2. Now, I'm trying to get the x's to cancel out. Could you cancel out the y's? Absolutely. What I do is this. I look for whatever the smaller numbers are because it's going to be easier. Okay? Making 17 and 34 match will probably be more difficult than making 12 and 6 match. Well, the truth is for this problem, negative 2 will do the trick for both. But in most cases, you want to look for the smaller number. Go the easier route. But you have a choice. You can go with, you can cancel out the x's or the y's, whatever you want to. All right, so my goal is to cancel out the x's here. So I'm going to multiply the bottom line here by negative 2 and write a new system. Okay, so that's what the system looks like with the new equation in the bottom. And now you ask yourself, does anything cancel out now? Do I get lucky now? And the answer is we get more than just lucky. Something weird happens here. 12x minus 12x cancel out. Negative 34y and positive 34y also cancel out. And if everything cancels out, what's left on this side of the equation? You might say, well, what happens over here? Well, if there's nothing left, it's a 0. And on the right side, we get negative 60 plus 60, which is also 0. So we get 0 equals 0. Okay? And you might think, well, that means no solution. Actually, that means the opposite. What that actually means is that the two equations here, when you graph them, the lines are the same line. This is what's called an identity, and which means that they're the same line. So we say that not only do these lines touch, they're the same line, they're touching all the time. They're like the two lines here. I'll show you the graphic here. You might remember this from last time. I showed you that you could have two lines that were sitting right on top of each other. Okay, and we said that this was infinitely many solutions, an identity. So that's what we have here. And the thing is, we didn't know that because we didn't graph these, but you can tell an identity if you get a result like this. If you get something that has to be true all of the time, that means these lines are crossing all of the time. So if you get 0 equals 0, or 3 equals 3, or negative 1.7 equals negative 1.7, if you get an equation that has to be true and has no letters in it, okay, a number equal to itself, that's how you know you have an identity. That means that the two lines are the same line, even though they looked nothing alike, right? By the time we worked on them, we realized these are exactly the same lines. So we get an identity, we say this has infinitely many solutions. Okay, now we come to this problem. Now this problem doesn't have decimals. This problem has a bunch of fractions in it, okay? And what we want to do is clear the fractions, get everything to be, once again, whole numbers so that you have ax plus by equals c, where a is a whole number. It's not right now, it's a fraction. B is a whole number, but c is not, on top and on bottom. So how can we get all these fractions to go away? Well, in the last problem, we multiplied by 10, or 10 times 10, like 100 or 1,000, whatever number of decimal places we wanted to get rid of, we just multiplied by that power of 10. Well, for fractions are fractions because they have denominators, okay? In other words, you wouldn't have a fraction if you didn't have a denominator. So how can you get rid of the denominators? That would create whole numbers. Well, what you do is you look at all the denominators. Like in this top equation here, you have 5. There's no denominator here, so it's essentially a 1, right? And here's another 5. Pick a number, the least common multiple, again, the least common multiple of 5, 1, and 5. What's the smallest number that all three of those go into evenly? Well, clearly it's 5, right? 5 goes into 5, 1 goes into 5, 1 goes into everything, and 5 goes into 5. So that means I can use a 5 here. And if I multiply 5 times this fraction here, you can look at it one of two ways. You can either say I'm going to cancel out the 5s, okay, or you can realize that what you're really doing here is you're multiplying 5 times 4, which is 20, and then 1 times 5, which is 5, and you're getting 20 over 5, which is ultimately going to be 4, right? Same thing as canceling out. So we'll just multiply it out for now. And then 5, you don't really need the 1, by the way. I'm just showing you that, you can think of it that way. So 5 times 2y here would be 10y. And 5 times 38 over 5, okay, there's the equal, there's a negative. Well, once again, you can either think of it as crossing out the 5s, like canceling out the 5s, which will give you a 38, or you can do 5 times 38, get, what is that going to be, 190 over 5, which is back to 38, either way. But you're saying, hey, there's still a fraction here. Yeah, but that's a 4. So there you go, no more fractions. Okay, that's the trick. Pick the least common multiple of all the denominators in the fraction. In this case, the least common multiple, the LCM, for 5, 1, and 5 is 5. Now, what's the least common multiple for 3, 9, and 9 down here? 9. Yeah, 9 would work, right? So let's multiply all these by 9. Now, you can't cancel out that. That doesn't work anymore, so you do have to multiply by the top. Okay, 9 over 1 times 1 over 3. 9 over 1 is 9, and 1 over 3 is 3, so you get 9 over 3. X. And then 9, well, here you can cancel out the 9, so you can just go right to 7y. And here you can cancel out the 9s, you go right to negative 26. But you could also multiply by the top and then simplify later. You can see that right there, 9 over 3, that's just a 3, isn't it? So you get 3. Okay, and now you have a system with no fractions. Do I get lucky? Not yet. Okay, 4 and 3 don't cancel out, 10 and 7 don't cancel out. So what are their least common multiples? Well, the least common multiple between 4 and 3 is going to be 12. So I need to make these both a 12. What's the least common multiple between 10 and 7? I think it's going to be 70. There's nothing smaller than 70. They both go into evenly. So what you do is you pick the one with the smallest least common multiple. The x's don't have to get as big as the y's in order to match up. So let's focus on getting the x's to be the same so they'll cancel out. Let's focus on getting them both to become 12s. Well, in order to get this to become a 12, I need to multiply this whole equation here by a 3. In order to make this become a 12, this needs to be multiplied by 4. But here's the thing. This is going to give me 12x, and this is going to give me 12x. One of them has to be negative if I expect to cancel anything out. So let's make the bottom one in the negative. That'll make this a negative 12. So 3 times 4x is 12x. 3 times 10x is 30y, I'm sorry. And 3 times negative 38 is negative 90 plus 24, negative 114. On the bottom, this becomes negative 12x. This becomes negative 28y. And negative 4 times negative 26 is going to be positive 104. Let's take these two equations in red and make a new system out of them. Okay, and that's done now. And now let's take a look and see, do we get lucky? Yes, the 12s will now cancel out. Well, we didn't get lucky. This time we made it happen. So 30y minus 28y is 2y. And negative 114 plus 104, or you could read it backwards. 104 minus 114 is negative 10. Divide them both by 2 and you get y equals negative 5. Okay? We have one of the letters done. We still need to find the x. Okay? To find the x, you usually take the negative 5, plug it into y in the original equation. But since the original equation has fractions in it, you can go ahead and use one of the ones that doesn't have fractions, because these are all equivalent, meaning you can use these over here. So I'll just choose the, I don't know, the bottom one looks like it's a little bit smaller number, so I'll use the bottom one. So 3x plus 7 blank equals negative 26, and we said that the blank, the y, is negative 5. So we get this, 3x minus 35 equals negative 26. We can add 35 to both sides to get rid of that negative 35. All right? We get 3x equals, whoop, that's supposed to be plus right there. And what is 36 minus 25? It's 9, so x equals 3. So what's my answer? Alphabetically, x comma y is 3 comma negative 5. Okay, so that's how to get rid of fractions. Multiply by the least common multiple of all the denominators. How to get rid of decimals. Multiply by whatever multiple of 10 you need to get rid of the decimals. Okay, and that's that. So let's go to the last thing here, special cases. And I actually just did one of the special cases a few minutes ago where we had an identity. If you're doing substitution or elimination and you get a weird result, like over here we got 0 equals 0, remember that? And the reason why we got it was that it turned out that they were both the same line. Well, that happened during elimination. It can also happen during substitution. And if it happens, then you know you have an identity. The other thing that can possibly happen, besides an identity, is when they're parallel lines and they never touch like that. So we saw this in the lesson yesterday. We saw that, you know, if you graph it, you can see that they're parallel and they don't touch. But what if you don't graph it? What if you're just doing your work? How would you know that you have what's called an inconsistent system, meaning no solution? So here's the same two equations, but no graph this time. You look at it and you go, okay, do I have a formula? And the answer is yes. I have two formulas. So that means I can use substitution. I don't need to use elimination. And which formula will I use? I'll use the top one. Okay, the top one tells me that y equals this stuff right here. If the top y equals negative 2x plus 7, then so does the bottom y. So you could take this and plug it in or substitute for y, and you get negative 2x plus 7 equals negative 2x plus 1. No more y's, so you've eliminated the y's by substitution. And now what you're going to do is try to solve for x. Well, you can't really solve for x if there's x's on both sides of the equation, so we get rid of one of the x's. Let's get rid of this one over here. How do you get rid of negative 2x? You're going to add 2x to it, and that'll cancel it out. But if you do that to the left, you have to also do that to the right. But that also cancels that out. So now what do you have now? You have 7 equals 1. And I don't know about you, but 7 does not equal 1. Okay? That is truly false. Patently false. That is not true. That is not going to work. So what this thing is telling you is that where do these two lines cross? They cross whenever 7 equals 1, which is never. They never cross. So if you get, unless you've made a mistake, as long as you've done your work correctly and you haven't made any mistakes, if you get something that's impossible, like 7 equals 1 or 3 equals 2 or 0 equals 7, anything that's not true, then you have no solution at all. There's no place where these things cross, and we call this an inconsistent system. Okay, and this works for substitution or elimination. So with either case, if you get to the point where you lose all of your x's and all of your y's, you have no letters left, just numbers, and the two numbers on either side of the equal sign don't match, that's impossible. And that means these never cross. And you can see graphically that's true. They never do cross, do they? All right. Here we have an identity. Now we already did one of the identities, but we'll just do this one really, really quickly here. These two lines are the same line. You can see it on the graph. It's really easy to see an inconsistent and identity on a graph. But if you're just given this problem here, you may not realize that right away. Okay? So we look at this, we go, okay, we're going to use elimination here. And what's the least common multiple between 2 and 4? It's 4. What's the least common multiple between, this is a 1 right here, between 1 and 2? It's 2. So you know what? I think it'll be easier to go for the y's. Let's make the y's both 2's. To make this a 2y, and this is already a 2y, so I don't have to change anything here. Okay? One of them has to be negative, so let's make the top one negative. What do I have to do to this y to make it a negative 2y? I'm going to multiply it by negative 2. What do I have to do to this 2y to make it 2y? Nothing. So I'm not going to multiply the bottom by anything, because I don't need to. So let's do that. Let's multiply the top line here by negative 2. This is going to be negative 2 times 2x is negative 4x. This is going to be negative 2y, which we already knew, equals negative 14. On the bottom, we're not multiplying by anything, so just leave that one alone. And now you have your new system. Now let's see if we get lucky. Does anything cancel out? Well, that cancels out. And that cancels out, leaving us with absolutely nothing on this side of the equation. And on this side, negative 14 and 14 cancel out, giving you that. So you get something that's true all of the time. 0 equals 0 is always, always true. It's not false all the time like 7 equals 1. Okay, 7 equals 1, that was always false. This is always true. And if you get something that's always true, that's an identity. And we say it has infinitely many solutions. So be on the lookout for those two possible outcomes. Infinitely many solutions. And that's it for that one there. So once again, just to recap, if you have a situation where you get something equal to itself, 3 equals 3, 5 equals 5, 7 equals 7, that means it's an identity, and the two lines are the same line sitting on top of each other, and they're touching an infinite number of times. Infinitely many solutions. If you get something that's impossible, like 7 equals 1, that's never true. 3 equals 7, 2 equals -4, whatever. Then, unless you've made a mistake, that means there's no solution. The lines must be parallel and not touching. Ever. Okay. All right, we're done. I'll see you at the next video.